All right, so in this video, we're going to look at taking our region of bounded by y equals 3x plus 1, y equals 1, and x equals 2. Same region we did in the last two videos, but now we're going to rotate it around the line y equals 1. So just to highlight that on here, this is the line y equals 1, that we're going to rotate this region around this way. So this is a little bit different than the previous ones. We have to think about what the best method is, again, by thinking about not the fact that this is a y equals something, but the baseline is the as I said in a previous video, you want to think about it in terms of the variable of the function and the axis you're rotating it around. When you're dealing with a function that's offset from one of the axes, you have to think about it in terms of what axis is this parallel to. And this is parallel to the x-axis. Y equals 1 is parallel to the x-axis. So we're going to treat it like it's rotating around the x-axis. That's the orientation of our function. And that's going to change the way that we set up our heights and radii and things like that. But it doesn't change the procedure. So because we're rotating around a line parallel to the x-axis, we want to use, because we have a function of x originally, we want to use the washer method. Remember, function of x, rotate around x. And so this is going to behave very similarly. Now, the thing that we're going to have to do is when we figure out our inner and outer radii, the inner radii is right here. It's 0. And because we're rotating around basically the bottom of our region. And then the outer radii R0 is not the height of this function per se, but it's the distance between the height of this function and the axis of rotation. So essentially what we're going to end up doing is we're going to take every function that in our inner and outer radius that we did when we rotated around the x-axis. And instead, what we're going to do is we're going to have to take away the distance that we've essentially moved our axis of rotation. Now, the sort of rule of thumb here basically is that we're going to take our function, in this case for the outer radius, minus the axis of rotation, which in this case is 1. Now, if the axis of rotation was y equals -1, then subtracting the axis of rotation would be minus -1, which would give us a +1, because if we were rotating around a line that was below the x-axis, we would be adding distance between the region and the axis of rotation. So subtracting that negative will get us the same thing. So again, think of this as the function minus the axis of rotation. And then we do the same thing for the inner function. The inner radius around the x-axis case was 1, but now we're taking that function and we're subtracting the axis of rotation, which is in this case also 1. And so what we're getting is 1 minus 1, which confirms this idea that the region is now actually touching the axis of rotation. So we've converted this washer method essentially into a disk method because the region is now touching the axis of rotation. Now, when you do this arithmetic, again, don't try to FOIL this before you simplify inside the parentheses. 3x plus 1 minus 1 is going to get you just 3x, and 1 minus 1 is going to give you 0. And so what we end up with is 9x squared. Our limits are in x in this orientation, so from 0 to 2, and then this is a very easy integration. 9x squared becomes 3x cubed. You plug in your 2, you get 24, and 24 times pi is 24 pi. So that's our solution. Now, we can't do this by the shell method, but we have to set up the algebra. The shell method, again, we're rotating around a line parallel to the x-axis. So we treat it like the x-axis. That means that we have to use the y variable to do our integration. And so we have to, as we did in previous examples, we have to solve for x in terms of y. And then we want to think about how do we set up our problem. So in our problem, we still have to deal with, and let's change colors here. So we still have to deal with this issue of the height. So this part hasn't actually changed. The height of the cylinder at any point that we're rotating it is the difference between the rightmost function and the leftmost function. Good. Now, the radius then is not going all the way to the x-axis. It's only going to y equals 1. So if we think about this in terms of this old radius was y, we're not actually going all the way to y, we're only going to y equals 1. So the radius is now actually just y minus 1. Because if I'm rotating around a point at, let's say, y equals 4, then my radius is only 3 because I'm only going from 4 to 1, not from 4 to 0. So y minus 1 becomes my radius. Now, the order that you do the subtraction in, it's going to depend on your orientation relative to the region. You're going to have to think about it sometimes, but in general, if you subtract in the wrong order, you're just going to get a negative sign. It's not really going to change the value of the magnitude of your result. And so if you subtract in the wrong order and you get a negative sign at the end, throw it away because you just subtracted in the wrong order. It should be the right answer if you didn't make any other errors. But in this case, it is y minus 1, and we'll get a positive answer when we do the work. All right, so we've set up our problem. So the difference, remember, the rightmost function was x equals 2. The leftmost function is the line 1/3 times y minus 1. That's our height. That's still true. That part hasn't changed in the shell method. What has changed is the radius, and that's become y minus 1. Now that's going to make our algebra a lot crazier, but because we're going to have to FOIL, but it is what it is. So we go through and we do the math. So we distribute the 1/3 here, the negative 1/3, and then we need to combine like terms. 2 plus 1/3 is 7/3. Here's our minus 1/3. Then what I did was I pulled out this 1/3 just to make my life a little easier. And so pulling out the 1/3 from the 1 factor, I pull it all the way out of the integral so that I have 7 minus y instead of 7/3 minus 1/3 y. And then I have to FOIL y minus 1 and 7 minus y. FOIL, get 4 terms. Simplify. The only 2 terms that add together are y and 7y to get 8y. Now, my limits of integration are, of course, in the y direction, which is y equals 1. It's based on my region. Y equals 1 and y equals 7. And then when I integrate this, I get y squared over 2 times 8 is 4y squared. Y squared becomes 1/3 y cubed. 7 becomes 7y, and I plug in 1 and 7. 4 times 49 is 196. 7 cubed is 343 over 3. 7 times 7 is 49. And then we subtract, plugging in 1. So plug in 1, I get 4, so minus 4. Plug in 1, I get minus 1/3, but I'm subtracting, so plus 1/3. Plug in 1, I get minus 7, but I'm subtracting, so plus 7. And when you add up this whole mess of terms, what you end up with is 36. 36 times 2/3 is 24. And just like before, I ended up with 24 pi. Now, again, the purpose of doing it both ways partly is to confirm that, yes, we do get the same answer. But it's, again, it's design. I'm doing this in order to particularly illustrate not just the worked example portion and how things can get more complicated, but the fact that there is a better method. And the better of the two methods is, in this case, the washer method. Not only is there less algebra, but the work that you have to do when you get to the end is less messy. It is easier to get to the answer if you choose the correct method than if you choose the incorrect method. You will get there, again, assuming you don't make arithmetic mistakes in all of these steps. But you should get the correct answer. But this is clearly an easier calculation than all of this. All right, we have one more to do, and that is to rotate around x equals a constant.